Okay, yeah, let's look at another gate. We're going to look at the inclusive NOR gate today. Inclusive NOR gate, remember we started off, we've been doing gates for a little while now. We started off with what? With the NOT gate. We looked at all the what? We looked at the truth tables, we looked at the switch circuits. We actually dealt with the circuit first, there it is on the board. And then we also looked at what? We looked at the Boolean equation for that. Then we also came and say, okay, let's look at the other case, and when we looked at what? At the DL and TL what? AND gates. Then we said, okay, we combine the AND gate with the what? We combine the AND gate with the NOT gate, and we get what? We get a NAND gate. We've looked at all that. Now today we're going to look at the what? We're going to look at the NOR gate, but we're going to start off with what? With the OR gate. We're going to start off with the OR gate, and what we're going to do is we're going to say, I don't want this input output here. Right, this is our OR gate. All we do is just pull our NOT gate. I want to pull, not erase. Just pull our NOT gate and make it what? Combine that with the what? With the what called with the OR gate. We could do that. I don't want to do it like that. What I'll do is I will basically pull it, and there we are. Or we could have done the same with the what? With this gate here, and say on the output here, instead of what? We put, let's remove this little A here. Let's go to the one to first ungroup that. What I'll do is basically do this ungroup, and then remove the A. Probably do the same here. Alright, ungroup first, and then say let's remove the A, because A is now there. It was probably wrong for me to leave the ones here. It's one state. Alright, remember we have other states. So if we do this here, we'll have what? We'll have a situation where whatever output we get here is going to be inverted. Alright, so remember that as long as we had a 1 anyway, if we didn't have a 1, our output was going to be 0, and that was going to be what? That was going to be inverted to a what? To a 1. So if you look at our truth table for this guy, it's 3 inputs, A, B, and C. We remember it's the 2 to the power of 3 will give us 8. It's the count 0 up to 7. So ultimately we have 0 up to 7. We are at 5 now. 6 and 7, 4, 2, 1. Now our output here, previously our gate only ended there, and if we had 0, 0, 0, there was nothing that was going to give us an output here. But this time now, our 0 here would then be changed to a 1. So this would then be a 1. But we saw that every time we had a 1 here anyway, that 1 will therefore turn its diode on, and that diode will allow current to come through, giving us an output here. But this case here, if we have a high output here, it will be inverted to a 0. So every other situation here is going to, the OR gate looked out for a 1. If it saw a 1, it gave us a 1. Now the NOT, the inverter, will invert that 1 to a 0. So this is the truth table for the what? This is the truth table for the NOR gate, for the 3 input NOR gate. Alright? Now, however, our output here now, yes, here it was A or B or C, but here it's going to be A or B or C, not. Alright, same as that there, the output here, this would have been A or B or C, but the ultimate output after the inverter will be A or B or C, not. What do we call this here? We call this our what? We call this our Boolean equation. This is the same as that, and these are the what? The Boolean equation. This is the Boolean equation for the inclusive NOR gate. So what do we have? We've got the circuit themselves, just a combination. Obviously, we wouldn't do this for this specific one. We can't have two VCCs, even though there's no crime. But it shows you that we could have just hooked up. We could have, instead of doing that, we could have just, yes, there's no crime. It means the same. But for clarity, we could just hook up that one VCC to come there. All right. So what you have there, you have a combination of an OR with a NOT. So it's going to be NOT OR. It includes states that are not what? That are not OR. This is not OR, it's NAND. So it includes those states. So it's an inclusive NOR gate. One last thing that we want to show is probably the what? The switch circuit. If we have a source, how would you represent this with switches here? We have a source. Remember that we need to protect. Remember that the NOT gate is actually a what? A parallel. So if we are parallel to the load, we expose to our source to the possibility of what? Of a short. So what we have here is 3 parallel switches. One would have been a NOT. One would have been a NOT. As it is, this is a NOT. This is how our switch circuit for the NOT looked like. Now, what then happens is that this is our output. So this would have been our NOT gate with only one input. This is our NOT gate, but here we are making it not this one, no, neither this one, no, that. For a 2 input, it would have been 2 parallel switches. For 3 input, like in our case here, this would be our B. And then, because we have 3 inputs here, our third one would have to be the other one. Now, this would be our C. So what have we done here? Our parallel circuit is the O, but now the parallel circuit has been made parallel to the what? Our parallel switches have been made parallel to the what? To the load. So at closing any one of them here is going to what? Is going to create a scenario where we are eliminating our what? Our output. Remember, if you close this or close that or close that, we actually shunt out our output. When you shunt out our output, it cannot have any what? It cannot go on. All right. So this here will be our supply, and this is what we call the switch equivalent circuit of an inclusive OR gate. I don't know, I think that was pretty easy. We've got 2 more gates to look at. We've got to look at the exclusive OR gate, but I will not be doing the circuits for the exclusive OR and exclusive NOR because they really get messy. They are actually quite huge. We can look at them on consultation if people want to know them. They are not really an issue. They are available on Google and everything, so it's not a real problem. But they are much tougher circuits to try and squeeze into the little periods. We try to keep our videos as short as possible. So, but I think for the basic gates we are almost done. We are left with what? With the exclusive OR and the exclusive NOR. I hope it's fun. I hope people are enjoying this. Sometimes I'm not enjoying it because sometimes I'm doing this in the cold, but I'm not a person who's fond of heaters and all that stuff. So no, in any event, it keeps you awake. If you put a heater here, I'll be dozing off in front of you. So I hope you're enjoying. I hope you're getting somewhere. Thank you so much. Till we meet with the what? With the exclusive OR gates.